Okay, welcome to Unit 8, Electrochemistry. As you can see in our unit of electrochemistry, we are going to be dealing with electricity. And sometimes, such in the case of batteries, electricity is actually a product of a chemical reaction. So we will be looking at those type of reactions that involve a flow of electrons when we study electrochemistry. So those types of reactions are called oxidation reduction reactions. Now, as you know, in chemical reactions, the goal is to get the octet, either by transferring or sharing electrons. So any reaction where there is a transferring, then that's called a redox reaction or an oxidation reduction reaction. And as you can see our definition here, it's where one or more atoms' oxidation state changes during the reaction. Now we're going to define exactly what we mean by oxidation state, but it's pretty similar to what we think of as charge. And so whenever at least one atom has a change in states between the reactant and the product side, then that is called an oxidation reduction reaction, or redox reaction for short. Now you see our two words here, oxidation and reduction. These are important terms to make sure you know. Oxidation refers to any time somebody is losing electrons through the course of a chemical reaction. And we say that their oxidation state increases. If you think about a charge, if somebody loses electrons, their charge will actually go up, because maybe they're 0 to start with. When they lose an electron, now they become +1 or +2. So the more electrons they lose, the higher their charge gets. So the higher their oxidation state will get. And the other term is reduction. Reduction refers to the other guy who is gaining the electrons. And when you're gaining electrons, your charge becomes more negative. So the oxidation state actually goes down. It goes from 0 to -1 if you gain an electron, down to -2 if you gain another electron. So that's actually where the word reduction comes from. It's because the charge is reduced as you are gaining electrons. Now, to help you remember these terms, I want you to think about this picture. This, of course, is an oil rig. So this is an acronym for oxidation is loss of electrons, and rig is reduction is gain of electrons. These are important terms to make sure that you keep straight. So just remember our oil rig to help keep them straight. So if we look at an example here, we have magnesium, which has its 2 valence electrons. Oxygen has 6. So when these guys get together, magnesium transfers 2 of its electrons to the oxygen, and we have the ionic compound magnesium oxide produced, and each element now gets their octet. Magnesium has completely lost its 2 valence electrons, so it has a +2 charge, and the oxygen has completely gained the 2 electrons, so it has a -2 charge. So we definitely have a transfer of electrons in this reaction. In this case, magnesium has been oxidized. Remember, magnesium lost its electrons, so oxidation is lost, oil rig. So with the oil there, we say the magnesium was oxidized, or in the passive term, we say the magnesium has undergone oxidation. It's no coincidence that it was reacted with oxygen, so it's been oxidized, because oxygen tends to take electrons away from people, but it doesn't always have to be reacting with oxygen to be oxidized. Anytime you're losing electrons, you are oxidized. Now, of course, the oxygen, on the other hand, is gaining the electrons, and so reduction is gain, and so in this case we have our oxygen, which has undergone reduction in this reaction. So we talked about the term oxidation numbers. That is the same thing as oxidation state. Those terms may be used synonymously. Now, if you have an ionic compound, this is a piece of cake, because for ionic compounds, the charge is the oxidation number. So if we have calcium chloride, of course calcium's +2, chloride's -1, so those are the oxidation numbers for those guys. Now it's only when you have polyatomic ions, or if you have covalent compounds, that's a little more tricky, because in that case there is no complete gaining or losing of electrons. They're sharing electrons, and we have to figure out who to assign the electrons to. So we have a set of rules to help us figure out who gets them. So one of the rules is that any element has an oxidation number of 0. We say that an element is neither gaining nor losing electrons, so it has oxidation numbers of 0. Even the diatomic elements, H2, O2, N2, they have perfectly equal electronegativities, so when they bond, no one loses, no one gains, oxidation numbers of 0. If you have a monatomic ion, again, like we said, that's a piece of cake, like the calcium and the chloride. The oxidation number is the same thing as the charge. It's when you have covalence that it is tricky, and there's sharing. Now, oxygen, since it has a very high electronegativity, one of the main rules that you will use a lot is that oxygen always gets to be the negative guy, and it's almost always going to be -2. Okay, except in cases where you have like hydrogen peroxide or Na2O2, always make oxygen -2, and that's usually the first thing to start with. Hydrogen, remember, it can be positive or negative, depending on the situation. Fluorine, as well as most of the other halogens, chlorine, bromine, they're going to be -1. If there's no oxygen present, you can figure those out. Also remember that since we are making compounds, you know that the charge on a compound always adds up to 0. Well, the same thing is true when you add up the oxidation numbers for any compound. They should all add up to 0. Now, if you have an ion, then when you add up your oxidation numbers, they should add up to whatever the charge on that ion is.
So for our first example, we're actually going to look at something that is an ion. We're looking at the dichromate ion here. Now you can see that overall it has a charge of -2. So when we add up the oxidation numbers that we assign, it must add up to -2. So first step, if you have oxygen, go with that first. Oxygen always gets priority to be the negative guy, and we're going to assume that it is -2. So since I have a total of 7 oxygens, that's 7 -2s, that means my negative total here is going to be -14. Now again, we said the whole thing has to add to -2. So if my negative total is 14, that means my positive total has to be 12. Now, I look at my positives, I have 2 chromium atoms, so if they have to add up to 12, that means each chromium must be +6. So we would say that the oxidation state, or the oxidation number of chromium, is +6. So 2 times +6 is 12, my 7 -2s is -14, 12 plus -14 equals the charge, in this case, of -2. So that's how we figure out oxidation numbers. So here's a few examples. I'd like you to pause the video and then assign what the oxidation numbers are to each of these guys. And then when you're ready, hit play and we'll see if you're right. Okay, now when you look at these, some of these were kind of easy. Some of these were a little bit trickier. So starting with the N2O5, that was a little tougher. But again, make oxygen priority to be the negative guy. So if I have 5 -2s, my negative total is -10, which means my positive total had to be +10. And since there's 2 nitrogens, and now normally we think of nitrogen as -3, it's nitride, but in this case oxygen gets priority to be the negative guy. That means we have to make nitrogen the positive guy, and so the nitrogen has to have a +5 oxidation state in order for this to add up to 0. Now the other 2 that I have shown here, we have the aluminum oxide. That's just a straight old ionic compound. That should have been pretty easy for you, hopefully. The manganese dioxide, we know manganese can have a couple different charges. Again, you give priority to oxygen to be -2. That gives me a -4 total. That means the manganese had to be +4. Let's go down to the bottom to the carbonate ion. Now we know, again, there's an oxygen. I give it priority to be -2. Now I know it's an ion that has to have a -2 charge overall. So I have 3 -2s, so that means my negative side is -6. Well, in order for that to add up to -2, my positive total must be +4. So carbon gets to be the positive guy here. There's only 1 carbon atom. It's got to add up to +4, so that means it must have an oxidation state of +4. The aluminum nitrite. Now this is an ionic compound. So I know aluminum as an ion has a charge of +3. I know that nitrite is a -1 ion, so that piece of it adds up to -3. But within that, I have a polyatomic ion that has covalent bonds. So I've got to look at that separately. Now I know my nitrite as an ion has a -1 charge. So when I do the oxidation states here of the N and the O, it's got to add up to -1. Again, I start with the O. O gets priority to be the negative guy. We're going to make it -2. So 2 -2s means my negative total is -4. So that means nitrogen has to be the positive guy. And again, in order to add up to -1, my positive total has to be +3. Which means since there's only 1 nitrogen, it's got to add up to +3. The nitrogen in this compound has an oxidation state of +3. So the aluminum, oxidation state of +3. oxygen, oxidation state of -2, and the nitrogen, in this case, has an oxidation state of +3. So let's look at an example of an equation where we have this happening. So if we're looking at this and want to know, well, what is the oxidation state on each atom? We can look at the zinc. It's elemental zinc to start with, so all elements have oxidation states of 0. If we look at our hydrogen chloride, well, we can think of that as an ionic compound. Okay, we know hydrogen's +1, chloride is -1, so that works. Zinc chloride. Well, zinc, that's an ionic compound, so zinc has a charge of +2, which means its oxidation state is +2. Chloride has a charge of -1, and so if I have two -1s, that adds up to 0, so everything looks good. Hydrogen, now again, even though it's diatomic and if it's H2, all elements have oxidation states of 0. And so that one's not too hard. We would have been able to do that thinking just about charge, but that's the same thing in this case since these are all really ionic compounds. Now if we're trying to figure out who's undergoing what, we look at the zinc. Zinc starts out as 0 and then ends up on the other side of the arrow here as +2. So the zinc in this case is losing electrons. It must have lost 2 electrons in order to get a +2 charge. So losing, remember, oil oxidation is lost. So the zinc is undergoing oxidation. And that means somebody else must be being reduced. So let's see, well, who's being reduced? Well, it's not the chlorine because chlorine is -1 to start with, and chlorine's -1 on the other side. So that kept the same oxidation state. But if we look at the hydrogen started off with a +1 oxidation state, and it now has a oxidation state of 0. So that means that the hydrogen is undergoing reduction. Its charge went down from +1 to 0. Remember, reduction is gain. So the hydrogen must have gained an electron in this case. So that's kind of what you do to figure out who's being oxidized, who's being reduced. Figure out the oxidation numbers before and after, and look to see who is changing. Okay. Now, there's all kinds of reactions that fit this category of redox reactions. Some synthesis reactions are redox reactions. We already looked at the magnesium oxide example before. To start off with, everyone has an oxidation state of 0. Now, in order to qualify as a redox reaction, that means there needs to be somebody who is changing their oxidation state. That means they have one oxidation state as a reactant, but that element has a different oxidation state on the product side. So in this case, to start with, everybody is 0, but on the other side, we can see, yes, magnesium changed its oxidation state. It lost electrons. Reduction, the oxygen was reduced. It gained electrons. So that is an example of a redox reaction. The decomposition reaction here. We've got the potassium chlorate. Potassium is +1 to start with. The oxidation, of course, the oxygen gets to be -2. If you do your math on this one, you find out that the chlorine has an oxidation state of +5 to start with. So those are all of our starting oxidation states. On the other side, well, KCl, that's just an ionic compound, so potassium must be +1. In this case, the chloride has a -1 charge, and again, we have the element oxygen. All elements are 0. So in this case, if we want to figure out, well, who was oxidized? Oil, oxidation is lost. Who was losing electrons? Well, the potassium didn't do anything. It started +1, ended up +1. But if we look at in this case, if we look at the chlorine started off as +5, and it ended up being -1. So it actually gained electrons. But the oxygen started out as -2, but it went down to 0 on the other side. So that means the oxygen, in this case, actually lost electrons. So the oxygen actually was oxidized in this case. It underwent oxidation. And the chlorine, as we said, the chlorine actually gained 6. And so its oxidation number went down, so it was reduced. Okay. Combustion reactions, if we look at this one, we'll see that, again, we have oxygen is definitely changing. It starts out as the element oxygen being 0, and then on the other side, we see it in compounds. It's going to have an oxidation state of -2. So as long as somebody is changing their oxidation state, then it qualifies as a redox reaction. Now, one of the most common types that we use in electrochemistry are single replacement redox reactions. If we look here, we have our element zinc. It's 0. The copper, in this case, has a +2 charge, which means it has a +2 oxidation state. Our chloride's -1. Now, on the other side, the zinc is now +2. Chloride is still -1. And now the copper is the element copper now, which means it has a 0 oxidation state. So in this case, if we look at the copper, well, what happened to it? Okay, well, it started out as +2, ended up being 0. So that means it must have gained electrons in order to do that. Its charge actually went down. It went from a +2 all the way down to a 0. So reduction is gained. So the copper was reduced in this case. And then the zinc started out as 0. It ended up as +2. That means it must have lost 2 electrons to get a +2 charge. Oxidation is lost, so the zinc was oxidized. The chlorine in this case did not do anything. Start off as -1, it ended up as -1. So again, we had a change. There was oxidation and reduction happening here, so this is a redox reaction. So I have 3 examples here. One of these is not a redox reaction. So take a minute, pause the video, look at all 3 of these, look at the oxidation states of each one, and see if you can find one case where the oxidation states are not changing. Because if they are, it's a redox. All right, let's see how you did. If we look at these guys, in A, just tag in bromine here. To start off with, it's an element, which means it's got a 0 oxidation state, and I can see on the other side it's -1. So we have a change happening there. So A definitely is a redox reaction. I don't have to go any farther than that. If I look at B, if I start looking at the copper, I can see it's the element copper to start with. Means it has an oxidation state of 0. And on the other side, I look at my copper. Well, it's got a +2 charge, +2 oxidation state. So it changed oxidation state. So that means that is a redox reaction. So I'm hoping C is the answer here. Let's look at C. To start with, I have my hydrogen. And here the hydrogen has a +1 charge. So it's oxidation state of +1. And on the other side, it's in water. Well, the O is -2. That means my hydrogen is still +1. Okay, so no change there. Carbon. Oxidation state of +4 on this side. If you do the math, you can work it out if you want to. On the other side, it's CO2. The O would be -2 times 2 is a -4 total, which means carbon has to be the positive guy. There's only one carbon, so the carbon is +4 oxidation state on this side. So the carbon did not change its oxidation states. That means my last guy is oxygen. This is not looking too good here because here's oxygen in a compound. It's going to be -2. Here I have my oxygen in the water. That's also going to be -2. And here my oxygen's in another compound, which means it's -2. So in this case, everybody has the same oxidation state on the reactant side as they do on the product side. So that means this is the answer to my question. That one is not a redox reaction. So hopefully that helped you out. Hopefully you'll be able to do all of your worksheet easily now. If not, we'll see you in class tomorrow. Let me know what questions you have.